When we look at a heavy industrial magnet holding a massive iron weight, we assume its strength is a frozen, unchanging state of nature. We stick it to a surface and expect it to hold that exact force forever. This chart shows what happens to a magnet, even in a perfect room temperature environment, away from any external disturbances. Over 100,000 hours, there is a microscopic, continuous decline in magnetic flux. In everyday life, you'd never notice this drop, but in precision technology, like high-temperature motors or the dynamic machinery inside aerospace components, this gradual decline, known as magnetic viscosity, leads to calibration drift or outright mechanical failure. This loss occurs at the structural level. Individual atoms remain magnetic, but the microscopic magnetic domains slowly rearrange or reverse, weakening the overall field. What we call permanence is actually metastability. The magnetic structure is highly stable, but it's trapped, a configuration constantly trying to escape into a lower energy state. Inside the metal, a ferromagnetic material is divided into tiny distinct regions called domains. Here, magnetic moments are forced into a unified alignment. They stay aligned because microscopic structures, like grain boundaries, create physical energy barriers. This resistance to reversing direction is called coercivity. These barriers are under constant attack from ambient heat. Thermal energy causes atoms to continuously vibrate, testing the coercivity. As temperature rises, vibrations become violent enough for a magnetic region to hop the barrier and reverse alignment. Heat makes this decay faster. This relationship is a literal mathematical scorecard. The equation dictates exactly how long the magnetic shield will hold, based on the ratio of the barrier strength against the opposing thermal energy. This relentless thermal attack drives magnetic viscosity. It ensures that any permanent magnet, given enough time, experiences a slow relaxation of its strength. Heat isn't the only antagonist. Every magnetized object generates an internal field flowing exactly opposite to its own alignment. This demagnetizing field keeps the material under constant pressure to reverse, forcing tiny domain adjustments until a more stable balance is reached. Heat and internal fields cause a slow decay, but a massive external force can disrupt the system instantly. When an impact sends stress waves through the metal, it temporarily lowers energy barriers, allowing trapped domains to suddenly flip. In brittle magnets, a severe impact physically cracks the material, fracturing grain boundaries and irreversibly destroying the structural integrity, providing coercivity. This diagnostic matrix shows the difference. Stored in a quiet room, the barrier remains tall. Inside a hot motor, thermal energy spikes to cross it. And under sudden impact, the barrier itself is physically crushed. A permanent magnet exists in a state of active equilibrium, besieged from all sides by ambient heat, internal opposing fields, and external structural stress. Magnets don't wear out. Their strength is a fierce, stored configuration that simply looks for any excuse to relax. By understanding the physics of that relaxation, engineers can predict exactly how and when a magnet will degrade. For high-temperature environments, they select specific alloys with massive coercivity to act as an impenetrable energy shield. They design motor geometries to neutralize the magnet's self-demagnetizing tendencies and engineer housing to absorb shocks before they can shatter brittle magnetic grains. In reality, every single permanent magnet is a violent microscopic standoff, holding the line against the relentless laws of thermodynamics.